Reaction Simulations Series, Episode 1, Basic.
Hi, I'm Philip Kinane, and have spent the last 10 years at COMSOL catering to the simulation needs of the chemical engineering community. In chemical reaction engineering, the goal is to understand how chemical reactions influence a given process, and to use that knowledge to achieve goals in development and design. In the past, sophisticated modeling tools were privileges that only large companies could afford, whereas today realistic models of advanced systems are feasible for all engineers. Though the scales may differ significantly, the physical phenomena remain the same and can be represented by the well-known equations we learnt at school.
Let's take an example. Here we have reactants A and B entering a stir tank reactor, where they are mixed and exothermically react to produce the product C. Heat is a byproduct and may need to be removed. This is simple enough, but if we are to make an accurate model of this system for simulations, we need to consider the physical phenomena involved and how they interact with each other. So, to simulate a reacting system or process, a model needs to include transport phenomena and reaction kinetics. Transport phenomena can be grouped into mass, momentum, and energy transport. In our reactor, the reactions themselves are taking place in the bottom half of the tank. Stirring promotes momentum transport by turbulent flow and significantly affects the mass transport through convection. We also have energy transport from the exothermic reactions, which leaves the system as heat. But how do you go from a conceptual model to real results for real-world applications? Here we have an example from the automotive industry of a catalytic reactor that removes nitrogen oxide from a car's exhaust through the addition of ammonia. A second, parasitic reaction, also consumes ammonia, which means that higher amounts of this are required. Investigating the reaction kinetics is the first step in understanding this process, and we achieve this by defining the material and thermodynamic properties and running the simulation. We can now simulate a 1D plug-flow reactor model, which includes assumptions about heat, mass, and momentum transport to provide more information about our reactor system. A far more sophisticated model in 3D is, of course, the final goal, where a full description of the mass, energy, and momentum balances are integrated with the chemical kinetics. This leads to greater understanding and results we can use for optimizing the reactor's design and operational parameters. Over these past 10 years, we at COMSOL have seen time and again how these types of simulations have transformed the chemical process and systems industry.